Hi. In our previous video, we saw how capacitors behave when they are charged. So we apply an external potential difference and we have a resistor. Then we saw how the charge varies as a function of time across the capacitor because the potential difference is constant and the capacitance and the capacitance and the resistance. So we studied how the charge on the capacitor accumulates over time. We saw that. Now another case is possible, right? How does it discharge over time? So you connect a capacitor and you join it with a resistor because you add up the resistances, so you get a resistance, okay? Or you join it with the resistor and it discharges. The charge will dissipate. So in this video, that's what we'll study. We'll study how charge dissipates or how capacitor discharges. Let me draw what happens. So this is a capacitor, okay, and we connect it with the resistor. Fine. And what we'll do is this has some charge accumulated on it, and this will the charge will gradually decrease and we'll get a current. So let us say this is the direction of a current. I goes there, I. Fine. So since it goes like this, we will be positive Q, negative Q, with Q. Now let me label these things. So this capacitor has a capacitance. Let us call this C, current I, resistance R. Okay, great. Now we need to relate the charge Q, current, the resistance, and I. This will be useful. Now what we can do is we can write Kirchhoff's law. Okay. So as I goes there, it faces a potential drop. Potential drop drops across a resistor. So we write this plus Ri, then it faces an increase. So we write minus, what is the potential difference across the capacitor? Charge by capacitance. Right, that's what it's the formula. And across this loop, so the loop is completed, you get 0. So from this we can immediately write Ri is nothing but Q by C. Now if you know what's I, you can easily see a differential equation. Right? I is nothing but dq by dt, the rate of change of charge per unit time. Now the important thing is that since the charge will decrease, so this dq will be negative. As time increases, the charge decreases, which gives our dq change in charge negative. So we write a minus sign there. This will help. So we substitute I is equal to dq by dt minus dq by dt. In this case, we get minus I dq by dt is nothing but q by c. Now this one is very easy to solve. We get dq by q is nothing but minus dt by rc. Easy. And now we need to sum up all these small changes, sum up all these small continuous changes. So we integrate, okay, so integral dq by q, okay, we will see what the limits are, okay, minus q by rc. Now what are these limits? Let us see what the limits are. So at time t equal to 0, at initial, we say 0, at time t equal to 0, the charge on the capacitor, let us call this capital Q. So initially capital Q is this charge on this capacitor. Now at time equal to say t, at a general time t, the charge on the capacitor, let us say it's Q. So after time t, q charge is left. So limits will be from q to capital Q from 0 to time t. Fine. And what do we want? We want our charge as a function of time. So how, as time increases, how does our charge vary? Now we can integrate. This is again an easy integration. Dq by q. So integral of dq by q is nothing but ln, like natural log with base e. So from this we can write the limit should be initial is q and the final is small q. It will be from this will be, and it's minus t by rc. Integral of dt is nothing but t. Now we're still not in a convenient form, so we raised both of them to the both sides to the power e. So we get q by capital Q is minus t by e to the power minus t by rc, raising both of them to the power e. From this we immediately get that q as initial charge is e to the power minus t by rc. That's what we get. So that's how a charge varies as a function of time. So it's e to the power minus t. That's how it varies. Now if you notice something, notice this term, right? This one right here. If you watch a previous video on how capacitor charges, this term has the dimensions of time. We showed this earlier. And this thing, RC, is known as, that's right, time constant. So we write this as tau, time constant. Another way to write this is that q initial charge q e to the power minus t by tau. Okay. Another important way to write, which gives, of course, tau as RC. Immediately follows. So that's how mathematically charges as a function of as a function of time. Now how does the graph of this looks? Let us see. Get about this. Okay. So I boxed the 3 important things you want to keep in mind. So let me draw this graph. So this is a charge q versus time graph. Okay. Let us say initially this has some charge capital Q. Now how does this vary with time? So if you graph this one, so this is time, so how it varies with time, that's how it will look. Yeah, that's how graph will look. And then we can make these tau, this is 2 time constant, 3 time constants, 4 time constants, and so on. An important case is, a very frequently occurring case is, how much charge is left when after 1 time constant, after a time equal to tau, after 1 time constant. We can easily show this, just like we showed this in previous video. There's nothing, the q, from this we can get q is initial capital Q e to the power t by tau, but they both are equal, so it's e to the power minus 1, which is q by e, and e is 2.718, like something. So we get, substituting this, we get q is 0.37 q. That's how much charge remains on the capacitor after 1 time constant. So if you kind of mark this, this will be 0.37 Q after one time constant. Now if you notice this graph, this line will not touch the time axis. Okay, this line will come closer and closer and closer, but it won't touch. So we say it touches at infinity. What can you conclude? That in theory, a capacitor gets discharged after infinite amount of time. So it takes an infinite amount of time for a capacitor to get completely discharged. But in practice, it takes about 4 to 5 time constants for 99% of discharge. That's what we use. So that's it for this video. And my questions to you are, so we know how charge varies, okay. From this we can easily show how does current vary as a function of time. That's one question, question 1. And second question is, how does the potential difference across this resistor vary? So enjoy solving these questions, and I hope you like this one.